Hey guys, today we're looking at rational functions. 4.4 kind of switches gears a little bit, and we're going to start looking at rational functions for the rest of the unit. So we've got a definition right here. It says a rational function is a function of the form r of x is equal to p of x over q of x, where p and q are polynomial functions, and q is not the zero polynomial. So we're looking at fractions. And we have polynomials in the top and polynomials in the bottom. So remember, a polynomial could have x in it, it could not have x in it. But what really is important here is that the bottom is not the zero polynomial. The bottom is not zero. We cannot divide by zero, so the bottom cannot be zero. It says the domain of a rational function is a set of all real numbers except those which make the denominator q 0. So for 1 right here, where it says find the domain of the following rational functions, we're going to figure out what would make the denominator 0, and then it's going to be everything except for that. So for my first one over here, my denominator is x plus 5. So to figure out what would make it 0, I'm just going to set it equal to 0. So I'm going to say x plus 5 cannot equal 0. I would subtract 5 from both sides, so x cannot equal negative 5. So when I write my domain, I could go from negative infinity to negative 5, union negative 5 to infinity. Or I could write it with my set builder notation, and I would say x is an element of the real numbers, and x cannot equal negative 5. Okay, for my next one, I've got x squared minus 4, so same idea. I'm going to take that x squared minus 4 and say that that cannot equal 0. So for this one, you can either factor or you can solve, just like we did the other one. If I solve, I'm going to add 4 to both sides. So x squared cannot equal 4. And then when I square root both sides, x cannot equal plus or minus 2. Remember, if you take the square root of both sides, you've got to put a plus or minus with it. So my domain is going to go from negative infinity to negative 2, then negative 2 to 2, and then 2 to positive infinity. Or I could say that it is x is an element of the real numbers, and x cannot equal negative 2 or positive 2. That's two different ways you could write it. Make sure you're paying attention to how it tells you to write it. If it says interval notation, that's when you use your parentheses and unions. If it says inequality notation or set builder notation, that is when you would go with the x cannot equal. Now, if I look at my next one, I've got x squared plus 1. So I'm going to put x squared plus 1 cannot equal 0. I'm going to subtract 1 from both sides. So x squared cannot equal negative 1. And this time when I take the square root of both sides, I get x cannot equal plus or minus I. So I is an imaginary number or a complex number. And when it comes to our graph or our domain, complex numbers aren't really part of that. So if I'm trying to graph, normally on my xy coordinate, we don't have complex numbers in that. We're not doing a complex plane, we're doing a real plane. So when I talk about my domain would be from negative infinity to positive infinity, or I could write it just as all real numbers, because that complex number, that I, is not going to restrict my domain in any way. Any real number I plug in still works, so it's negative infinity to infinity. And then for my last one over here, I've got x squared plus 2x plus 1 cannot equal 0. So I'm going to do some big X factoring. I'm going to put a 1 on top and a 2 on bottom. So I need something that multiplies to 1 and adds to 2. That's going to be 1 and 1. So you could write it as x plus 1 times x plus 1, or you could just write it as x plus 1 squared. To solve this one, I can take the square root of both sides to get rid of that squared. So x plus 1 cannot equal 0. Now I didn't put a plus or minus here because 0 is not positive or negative, so it doesn't need a plus or minus. And then I can just subtract 1 from both sides. So x cannot equal -1. So when I write my domain, a little more room, I'm going to go from -infinity to -1, union -1 to infinity, or x is an element of the real numbers, and x cannot equal -1. So finding the domain is just figuring out what would make the bottom equal to 0, and then everything except for that. Now, if we have a graph, we can also find the domain and range. And then we're going to add on to this. We're not just going to find the domain and the range. We're also going to find the vertical and the horizontal asymptotes. So if I'm looking at my first graph, if I'm trying to find the domain, that's how far left and how far right my graph goes. So if I'm looking, this arrow over here means that it's going to go from -infinity, and it's going to stop once it gets to this dotted line right here, which is our vertical asymptote going at -3. So I'm going to go from -infinity to -3, then union -3, and my graph picks back up, my red line picks back up and goes off all the way to infinity. So we kind of already found our vertical asymptote, so I'm just going to put that right here as well. My vertical asymptote is going up and down at x equals -3. So notice my domain and my vertical asymptote kind of go hand in hand together. Whatever my domain restriction is, whatever's not in my domain is what my vertical asymptote is. Okay, then looking at my range, how far down and how far up my graph goes. So this arrow down here means that it goes down to -infinity. And it's kind of hard to tell because it kind of blends in with our axis, but we do have something going on here. It's not touching our axis. We've got a horizontal asymptote going across there at 0. So I'm going to go from -infinity to 0, union 0 to infinity. So then my horizontal asymptote would be at y equals 0. So just like my domain and my vertical asymptote go hand in hand, my range and my horizontal asymptote go hand in hand. So when I was looking for my domain restrictions in example 1, I was also finding my vertical asymptotes. Okay, we're going to look at the second graph over here. So on the second graph, we've got two vertical asymptotes this time. We've got one going up and down here and here. So my domain is going to go from -infinity to my first one at -4. Then I'm going to go from -4 to 4 because we do have this part in the middle right here that's kind of going down. And then I'm going to go from 4 to infinity. So when I'm looking for my vertical asymptotes, my vertical asymptotes are at x equals -4 and +4. You can write them together like that with a comma in between them, or you could write it x equals -4 and then x equals +4, two separate equations, whichever you would like to do. For my range, I gotta be careful here. So these arrows mean that I'm going to go all the way down to -infinity. But notice this middle section only goes up to 0. And I'm going to put a bracket with it because it does actually hit that 0. So you got to make sure you're being careful here. It doesn't go all the way up to my asymptote. Then I'm going to do a union. And then these endpoints do kind of go to my asymptote. So I'm going to go from 2 up to these arrows mean it's going to go up to infinity. So the range you got to be a little careful with. There might be a gap there sometimes. So just make sure you're paying attention to that. And then that does mean that my horizontal asymptote is going across at y equals 2. So when we're talking about rational functions, we are going to talk about how to graph them next set of notes. So when we're talking about graphing them, it's really important to know how to find these asymptotes because they're very key features, very important parts of your graph. So that's what we're going to look at on the back. And luckily, you already know how to find your vertical asymptotes because it's finding the domain restrictions that we've been doing since Unit 1. So that's what example 3 is. Finding vertical asymptotes is just setting the denominator equal to 0. So for my first one, my denominator is x minus 1. So this time, instead of saying x minus 1 can't equal 0, I'm actually looking for where it does equal 0. So I'm just going to say x minus 1 equals 0. I'm going to add 1 to both sides, so x equals 1 would be my vertical asymptote. For my second one over here, I've got x squared plus 4x minus 21. And when I set that one equal to 0, I do need to factor. So I'm going to put a negative 21 on the top of my x, a 4 on the bottom. Looking for two numbers that multiply to negative 21 and add to 4. That would be 7 and negative 3. So I'm going to have x plus 7 and x minus 3. So that means x plus 7 equals 0 and x minus 3 equals 0. Subtract 7 over here, so x equals negative 7. And add 3 over here, so x equals 3. So you've got two different ones here. And like I said, you can write them as two separate equations, or you could put them together and say x equals negative 7, comma 3, whichever way you prefer, totally fine. So finding your vertical asymptotes is just the same thing as finding the domain restrictions. You just don't actually have to write the domain after you solve for what the bottom equals 0, the denominator equals 0. Finding the horizontal asymptotes is where it's a little bit different. You've got three different cases that you're going to look at. So the first one is, well, all three of them are talking about the degree of the numerator versus the degree of the denominator. So the first one is a higher degree over a lower degree, and that means that there's no horizontal asymptote. The second one is a lower degree over a higher degree, and that means that your horizontal asymptote is going across at 0 on the axis. And the last one is if you have the same degree on top and bottom. And for that one, you're going to take your coefficients. So I've got a little rhyme for you to help you remember it. High over low, then no. Low over high, then 0 equals y. And same over same, coefficients are the game. So let's look at a couple of examples. So for f of x, we've got 2x squared minus 5x plus 2 over x squared minus 4. So the degree for the top is the highest exponent, which would be the 2x squared, quadratic. The degree for the bottom, x squared minus 4, would also be squared. So for this one, we've got same over same. So if it's a same over same, coefficients are the game. So I'm going to take the coefficient from the top and the coefficient from the bottom. The coefficient at the top is 2. The coefficient on the bottom is 1. Because there's not anything written, it's an understood 1. So I just divide them. 2 divided by 1 is 2, so my asymptote would go across at 2. For g of x, I've got x minus 1 over x squared minus 16. So for this one, it is a low over a high, a lower degree over a higher degree. So if I have low over high, then 0 equals y. So my asymptote is just going to go across at 0. And for h of x, I've got 3x to the fourth minus x squared and x cubed minus x squared plus 1. So for this one, I have got higher degree, x to the fourth, over lower degree, x cubed. So when I have a high over a low, that means there's no horizontal asymptote. There's no horizontal asymptote, but there is what we call an oblique asymptote or a slant asymptote. So an oblique or slant asymptote, we're not going to actually go through how to find those for our class, but we are going to talk about what they are, what they look like, and if you go into calculus, you will kind of look at them. But what it says is when the degree of the numerator of a rational function exceeds the degree of the denominator by 1, then the function has oblique asymptotes. In order to find these asymptotes, you need to use polynomial division, so long division or synthetic division, and the non-remainder portion of the function becomes the oblique asymptote. So an example of what this would look like, if this is my graph over here, you could still have a vertical asymptote, but what's going to happen is your asymptote is going to go at a slant like this instead of being a horizontal asymptote. So you'd have like a graph section down here and a section up here. So it's slanted instead of straight across. So to find that, you would use your polynomial division. And so that's how you would get like the non-remainder portion. So it would give you like a linear function. Okay, and then the last question that we're going to look at today is a word problem for rational functions. This one is called a work problem. So it's going to talk about people doing work together. So your formula for this is 1 over a part plus 1 over a part is equal to 1 over them doing it together. So this one says that Randy can finish his homework in 20 minutes working alone. Working together, Randy and Julie can finish the assignment in 11 minutes. How long would it take for Julie to finish the assignment working by herself? So if you're looking at this, we don't know how long it's going to take Julie to finish it, and that is one person just apart. So I'm going to do 1 over, let's say x for Julie. Then I know how long it takes Randy to do it by himself. It takes him 20 minutes, so 1 over 20. And then it's going to equal, and then working together, it takes them 11 minutes, so 1 over 11. Now, to try and solve this, I want to start by trying to get x by itself. So I'm going to start by subtracting 1 over 20. When I subtract this, I get down to 1 over x is equal to. Right here, the common denominator would be 220. So I would multiply this one by 20 on top and bottom, and this one by 11 on top and bottom. So 20 over 220 minus 11 over 220 is going to give me 9 over 220. And then we can cross multiply top times bottom and top times bottom. So x times 9 is going to give me 9x, and it's going to equal 1 times 220, which is just 220. Then I can divide both sides by 9, and I get down to x is equal to, generally we don't talk about time in fractions, so we wouldn't necessarily leave it as 220 over 9. We can change it to a decimal. For this one, we'll round it to 2 decimal places, so 24.44 minutes. When it comes to MyMathLab or your test, I will make sure that it specifies exactly what to round to, and MyMathLab will tell you exactly what to round to. So that's it for this set of notes. Let me know if you have any questions. Make sure you start your assignment that goes with this, and you guys have a good day.